So this set topic is a topic we have considered before, maybe whilst we are still in secondary school. It has to do with certainty and uncertainty of a certain event, of an event, certainty and uncertainty of an event. So what are we considering here? We are going to check, or we are going to inspect an event and check what is the likelihood of that event to occur, and also the likelihood of it not to occur. So please flow with me as we go into the class. So probability. I'm going to be very fast with this so that we'll not have to run through everything from the niche. I'm going to be very fast. It's taking this shape. So let's say probability. So I'm going to walk through this table. So we have the place of additive probability or addition. I'll have the place of multiplicative probability, multiplication. Under this additive probability, there are two events that is likely to occur here, and at the same time, under this multiplicative probability, there are two events also that is likely to occur here. Okay, this one will have mutually exclusive events. Mutually exclusive events. And here we have partially, you can call it partially dependent or partially, let's say partially dependent event. These are all names. Dependent event. Yeah, while under the multiplicative, we have what we call the dependent and independent event. So I'm going to have a quick ride around this. These are basic. These you want to run with. So the addition we have mutually exclusive, partially dependent. Under multiplicative, we have dependent event and independent event. So we are going straight into calculations. Addition is a simple probability we all know. Let's say they ask you what's the probability of getting a face when a coin is tossed twice. So you know the event is something discrete. We know in a coin we either had head or tail in a coin. We either had head or tail. What's the probability of getting an head when the coin is tossed? So we know that it's always in this 1/2. So assuming they tell you we want to get, when the thing is tossed twice, we want to get headed, and what's the probability of getting two heads? So we know we're going to have the event such as this: head, tail, head, tail. I'm sorry, I want to use this corner to explain that. Head, tail. So the event that is going to occur will be head. This place will be head, tail. Here will be tail, head. And here will be tail. So assuming they ask us, you can see what are the stuffs that occur when these two stuffs are tossed. We have 4 occurrences. And if we want to look for the probability of getting an head, it will just be 1/4. If we want to look for the probability of getting head and tail, it will just be 2 all over, because we have head and tail here, we also have head and tail. It will be 2/4. So these are simple probability. Take the additive rule, simple probabilities. So under the simple probability, we have mutually exclusive events. When an event is mutually exclusive, it means that you can be able to, if you want to check for the probability of that event occurring, you can be able to check for one and check for the other and bring them together. You check for one separately, you check for the other separately, and bring them together. But partially dependent, okay, example of this event, let's say you a discrete event like your coin, and when your ludo dies, when you toss a die once, let's say you roll a die once, what's the probability of 6 occurring? Is discrete. It's just 1/6. 6 cannot occur, especially when you are tossing just a dice. What's the probability of 8 and 7? What's the probability of 6 and 5 occurring? So it has to be, you look for the probability of 6 occurring, and you look for the probability of 5 occurring separately. So both events, they are mutually exclusive. They don't have anything really in common. They are distinct in themselves. But while for partially dependent events, there is something, they have something called here, let me use this word, intercept. Yeah, they have an intercept. If the probability of one occurring, let's say this is A and this is event B, if the probability of event A occurring is this, probability of event B occurring is this, but for partially dependent event, there is a place where both of them meet. It's called intercept. At this point, where both of them meet, is the intercept of A and B is going to be factored in whenever we are working with partially dependent event. We are going to see a question around that. At the same time, we'll check a simple question around it before we move to the bulk of the game, which is dependent and independent events. So work with me as I go through the mutually exclusive and partially dependent events. Okay, welcome back to class. So I was speaking before on addition theorem, additive probability. So we're going to check an example to be able to confirm that truth. It always takes this shape. They're asking you what is the tendency of a certain event to occur or a certain other events to occur within the same space. Yeah, within the same space. So like this one, they say what's the probability of A or B to occur, such that the probability of A and B to occur is equals to the sum of the two different probabilities and is equals to PA plus PB, that is the probability of A plus the probability of B. So we're going to check these are simple additive. These two events, they are called mutually exclusive events. That's why we're having the result as probability of A plus the probability of B. So we're going to check it to understand this. So the example we have here is one card is drawn from a pack of 52 cards. He said, what's the probability that it is either a king or a queen? Yeah, this. And many of us know how to use cards. Those cards that they do play. So we have in those cards, we have that pack of 52 cards. There are 4 kings and there are 4 queens inside. So now they are asking you, what's the probability of, if you select any card at random, what's the probability of that card that you selected? What's the probability of it being a king? That should be, since we have how many kings? We have number of kings. Let's start with saying number of kings is equals to 4. Number of queen is equals to 4. And the total number of cards is equals to 52. So they say, what's the probability of a king occurring? That should be probability of a king, P king, is equals to the number of kings over the total number of cards. It's as simple as it. Probability of king occurring, that will give you 4 over 52. So the probability of queen occurring will take the same format. It will be, let me just wipe it up. Okay. It will be probability of a queen is equals to the number of queen all over total number of cards, which is the same thing as 4 over 52 because we have 4 queens. We have 4 queens, we have 4 kings. So you need to study a card to know how many discrete stuff we have. For packs, we have spades, we have club, we have king, we have queen, and many others. You need to know them in their numbers to be able to understand all this stuff. Know how many numbers of this is contained in a pack of cards. So for this particular question, we're focusing on king and queen. So we have 4 kings and 4 queens. They are taking this separate. These are the probability of them occurring distinctly. But they ask you, what's the probability of it be either a king or a queen? So you are going to apply the addition theorem. You have to know the probability of a king occurring, that of a queen occurring. Then you add them together. So we're working with the word or. So whenever you hear the probability of an event occurring or the other occurring, you are using an additive theorem. So far, both events are mutually exclusive. You just add them together. So this one will now give us probability. Let me wipe it up. This is the probability. Probability of a king or queen is equals to 4 over 52 plus 4 over 52, giving you a total of 8 over 52. It's as simple as that. There's nothing more. You may want to break this down to get your simplest term. There's nothing more. So we'll just move to events that are partially. That is, one is intersecting with the other. The other event under addition theorem, there are 2 stuff I mentioned. One is mutually exclusive and the other one is partially dependent event. So we're going to check an example under that. So I'll quickly give an example. Let's say we want to draw a number from a random number of 1 to 50. We want to draw a number Okay, example, draw a number or draw a number that is divisible by 3 from a random number between 1 to 50. And we're looking for a number that is divisible by 3 from a random number between 1 to 50. So for you to get this one is simple. For you to get this, you have to know those numbers that are divisible by 3 within this range. Then divided by the total number of numbers that we are considering. This is 1 to 50. 1 to 50, the total number of numbers will be what? It will be 50 minus 1 plus 1. That's giving you 50 different numbers. Why the numbers that are divisible by 3 within this range? You have to check them. It starts with 3, 6, 9, we have 12, we have 15, it goes in that order up until, okay, let's do it together and see. We have the numbers solution. The numbers involve is equals to 3, we have 6, we have 9, we have 12, we have 15, we have 18, we have 21, we have 24, we have 27, we have 30, 33, we have 36, we have 39, we have 42, we have 45, we have 48. So in total, how many numbers are divisible by 3 here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 numbers divisible. All over the total numbers between 1 and 50 is equals to 50 minus 1 plus 1, which is equals to 50. So therefore, our probability of number divisible by 3 is equals to this number here we have, which is 16, all over the total number, which is 50. This is a simple probability. I want us to know this so that we can be able to explain further the exclusive event and the partially dependent event. What is the probability? The probability of getting a number divisible by 3 or 7 between 1 to 50. Okay, I've rephrased it this way. So we want to now understand exclusive events and partially dependent events. Solution. So we have already solved for numbers divisible by 3. Probability of getting, you need to know the probability of getting a numbers divisible by 3, which is equals to 16, which we check together, over 50. And we also need to know the probability of numbers. Probability of numbers divisible by 7. And that should give us 7 over 50. You may want to check it. 7, we have 14, we have 21, we have 28, we have 35, we have 42, and 49, making it 7 numbers. So they now ask you, what is the probability of getting a number divisible by 3 or 7? So that will give you, assuming these two events are mutually exclusive, you will just get 16 plus 7. You will just get, if they are mutually exclusive, which they are not, mutually exclusive, it will just be P3 or 7 should give you 16 over 50 plus 7 over 50. Then your total answer will just be 23 all over 50, which is not, because both events, they are not mutually exclusive. There are numbers in between the range that are also divisible by 3, at the same time divisible by 7. Numbers like what? We have 21. 21 can be divided by 3 and can also be divided by 7. And we also have numbers like 42, even 42 as well. 42 can be divided by 3, can also be divided by 7. So we have to consider all this whilst doing our probability. So cases like this, we'll have P, let me call P3 plus P7 minus P3 intersect 7. I'm just using this to explain it. Probability of 3 occurring, your probability of it being divisible by 3, probability of it being divisible by 7, and probability of it being divisible by 3 and 7. So we have just two numbers that fall into that ring, 21 and 42. So this will be 15 all over, this will be 16 all over 50 plus 7 all over 50 minus 2 all over 50. So after solving, the answer that you get will be equals to 21 over 50. Yeah, this is the final answer. This explains partially dependent events. So thank you. We are going straight to multiplicative theorem or multiplication theorem. So this multiplication theorem, we use the word both and often in multiplication theorem. For addition theorem, we use or. For multiplication theorem, we use both and. They ask you, what is the probability that both events will occur? We know it's multiplicative theorem. What is the probability of A and B to occur? You know it's multiplicative theorem. So I told you that multiplicative theorem, we have mutually independent events and we have mutually dependent events. Mutually independent and mutually dependent events. For mutually independent events, if they ask you what's the probability of A and B occurring, you know you are just multiplying them. You multiply the probability of A occurring alone and the probability of B occurring alone together. Why? For mutually dependent, whenever an event is dependent on the other to occur, for you to get the probability of both of them occurring, you have to know the probability of the single ones occurring, then the probability of the conditional probability of one occurring depending on the other. We're going to check a question around that. We'll check a question. So for this, it is discrete. For this other one is dependent on the other, just like the name sound, dependent event. Assuming they ask you, what is the probability of picking in the pack of 1 to 50? You want to pick one card, one number out of it. So they ask you, or they say you should pick two numbers, but differently, without replacements. Questions like that falls on that dependent event. Because if I pick one, that number I pick is certain, but the next number I'm going to pick will be depending on the first probability, because I've picked one. The number will no longer be 50 again. It will not be 49. Do you get? So picking the second number, it will be dependent on the number I picked before. So that is for dependent and independent events. It takes this formula. PA.PB is equals to PA intercept B. So for dependent event, PA intercept B is equals to PA dot P into bracket B all over A. What does this term mean? B all over A. It means this B is dependent on the occurrence of A. B at the top, the one at the top, is dependent on the occurrence of A. That is, A must have occurred before you can be able to know B. Do you get? It's as simple as that. It's as simple as that. So let's check an example. The first example we did an example that I say, what's the probability of getting a king and a queen? I said, what's the probability of getting a king and a queen from a pack of 52 cards? So we want to now check what is the probability. That other one was king or queen. For this case, what is the probability of getting a king or a queen? So we just know the probability of a king, P king, which we agreed that is equals to 4 over 52, while P queen, which we also agreed is equals to 4 over 52, because there are 4 kings and 4 queens. So P king queen, P king dot or and queen is equals to 4 over 52 times 4 over 52, which is equals to, this will give us what? This will give us 16 over 52. It's as simple as that. So for the second example we did, that we talked about a random number between 1 to 50. What's the probability of getting a number divisible by? What is the probability of getting a number that is divisible by 3 and 7? Let's check these other examples together. Assuming, okay, want to work with the other example, the one of king and queen, the king and queen example. Assuming both events are dependent on each other, that is, both events, when you want to pick the second event, it is dependent on the occurrence of the first event. For picking, we agreed that picking is equals to 4 over 52, right? So P queen, since we are looking for the probability of getting a king and a queen, so and be very, very intentional about the tenses I use. And we are looking for the probability of getting a king and a queen. So the probability of a queen will be equals to, queen is also 4, but the total number of cards left will be 51 because we have already picked one before for king. So it will be 51. So now the probability of getting a king and a queen will be equals to P king and a queen will be equals to 4 over 52 times 4 over 51, which will give us 16 all over 52 dot 51. It's as simple as it is. As you see, it is as simple as it is. We understand these particular aspects further when we move to Baye's theorem of inverse probability. Baye's theorem, we will be needing the knowledge of dependent probability. So I want you to know this and get it clear, especially with the one that has to do with an event depending on the occurrence of the other. That formula, this formula, I want it to stick to your memory. This formula that says probability of A intersect B, A and B occurring, is equals to PA dot PB over A. I want you to know this very well. That is, PB all over A is equals to PA intersect B over PA. This formula is very important. So we are going to be working with this formula throughout our Bayes theorem. In fact, this is where Bayes theorem starts for. This is the basic. This is the proof. We call it proof. This is the known statement. This is the basic from which Bayes theorem starts from. It's from this we move further. So we are going to be checking around Bayes theorem for our next class. Bayes theorem. Bayes theorem. So we're going to check a sample space. And we want to know why, I told you about dependent events. We want to know why this formula at this left-hand side is equal to the one at the right-hand side. That's questions that most likely will come out around Bayes theorem. They will say, proof this formula is the first question that you must see under Bayes theorem before we start checking examples. I told you about dependent events in our last class. I said you should note that formula very well. I was talking about PB all over A. That is, if it's PB all over A, it means probability of B depending on A. So in this case, we are going to check this. So from there, for us to be able to prove this one above, we have to have a known. We call it known. From known, you get the unknown. So this is our proof. So proof, probability of A all over H is equals to probability of A intersect H all over probability of H. So we want to check this. So what are the two things we'll be looking for to be able to interpret this statement? We'll be looking for the first one at the top, and as well, we'll be looking for the one at the bottom. We'll be looking for this. We'll be looking for these as well. We'll be looking for this one at the top and this one at the bottom. When we eventually get it, we'll put everything. We'll exactly be getting what we have here. That's where we are going. Very simple. Very simple. So for this one, this is probability of AI depending on H. So what is H? H itself, we'll get to know H, but H itself is the sum of exclusive events. That's what H signifies. Sum of exclusive events. Why this AI? AI is the original probability we are looking for. Original probability, they call it the priori. You can call it old probability. The original probability we are looking for, the priori. So the posterior probability is this very one. This one you are seeing here is the posterior. Posterior. I know you should have come across posterior. Why AI is priori or original probability. The one we are looking for, original probability. Original probability. Please don't mind my handwriting. Hope you get that's the reason why we're using sound. Original probability. Why this H? The H itself is sum of mutually exclusive events. Sum of. Why this A intersect H? It is called joint probability. Joint probability. Because if we cross multiply, PA intersect H will be equals to PAI all over H multiplied by PH. This PAI all over H can also be called conditional probability. That posterior probability can also be called conditional probability. So when you multiply this and this together, you eventually be getting this. So this one is called joint probability. The one at the numerator is called joint. I just want you to be familiar with all these words. It's called joint probability. So we are diving straight into the deep. So let's launch. Okay, welcome back. I told you we're about to launch deeper. We want to fly together. So this was the known I was telling you about. The known. You need this. You need to know this. This is where we are starting from before we are going to all other parts. So I told you the very part we are looking for is this top and this bottom. So we want to get PAI intersect H. I want to also get PH. I told you before that H is the sum of exclusive events. While PAI intersect H, it is called joint probability. So we are flying together. So from the top, I told you from dependent events, when both of them are dependent, PAI intersect H will be equal to PH over AI dot PAI. So why this is how you understand. Let me be very, very raw with you so that you can understand it in the term. Understanding is key. So if we're having PAI intersect H, it's taking the form of PH all over AI. Note, the one that will come after it must be the same. It will be the probability of the one at the bottom. It will be the probability of the one at the bottom. So PAI intersect H can also be written as PA if this AI, assuming, okay, for this, get this now. For this H all over AI, H is dependent on the occurrence of AI. In this case, AI is dependent on the occurrence of H. It's still the same joint probability. The same thing here. Joint probability of AI and H. You can either bet forth H all over AI or AI all over H. Whichever one you bet forth. Note that whatever will come next must be the probability of the one at the denominator. That's just it. So from this one, we want to prove that Baye'S theorem that we had. And I told you these are our known. Right? So now, we want to get the one at the numerator. Let's focus on the numerator first. So PAI intersect H. That will give us PAI intersect H. This one at the top. It will give you P of H over AI dot what will follow next. That will be my probability of the one at the denominator, PAI. So this is what is following next. So, and this one is equals to the joint probability. So we can easily replace this joint probability by this one at the top. Do you get? You know what AI means? AI can be A1, A2, A3, A4, A5. It can be anything as the case may be. So we can easily replace this one by the one at the top. This is from dependent events. So now for the one at the bottom, I told you that H is a simple proving. I told you, but you just have to state those stuff I defined for you. Your joint probability, your mutually exclusive, your priori, your posterior, and all those stuff, so that they will know you have something you are proving with. So your AI, your PA, I want to get for H. I told you H is the sum of exclusive events. H simply takes this shape, A1H plus A2H plus A3H plus ... plus ANH. That's what H means. H is the sum of exclusive events. So PH will not be the probability of that sum. So PH will be equals to P into bracket AIH. Sorry, not AI. This is A1. Don't confuse it. A1H plus your P, that's the probability of A2H plus ... plus probability of ANH. I'm sorry for that. ANH. You get that, right? So now we have successfully gotten the denominator aspect and we have gotten the numerator aspect. But we cannot leave this denominator aspect in these terms. Else it will be resembling what we have, because this one is still a joint probability. This PA1H is the same thing as saying PA intersect H. So we have to split it out. The same way we have splitted this one out. This joint probability, we splitted it out to this form. So if we are splitting this one out, this will give us what? Probability of H depending on A1 multiplied by the probability of A1. The same thing goes for this. The same thing goes for up until the end of it. So let me split it and show you. So we'll just factor it back into the main one, and we have gotten our answer. It's as simple as that. You know, at the denominator, we are having the sum of the probability from 1 up until n. Because I told you that is the sum of exclusive probability. That's the H, pH. And that pH we expressed it to be equals to P into bracket A1H plus P into bracket A2H plus dot 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 up until P into bracket ANH. So I told you that that A1H we have is called joint probability. We have to express it out. In expressing it out, PA1H is equals to PH all over A1 multiplied by PA1. You know, I told you that the one at the bottom must surface as the next one. So what this one simply means, it means the probability of H occurring depending on A1. So the same thing goes for A2. The same thing goes for AN. So after knowing all this, I want to put it back into that pH. You know, we have pH is equals to, so putting everything back into that pH. pH is at the bottom from the known, from the very place we started from. pH is at the bottom. So it now takes this form up until the nth value of it. Do you get? So while the one at the top, we have already expressed it first at the very first place. That because the one at the top, we are having PA intercept. The one at the top was the joint probability itself. This is the one at the top. Then it was equals to PAI intercept H. So I told you this one is called joint probability. When you want to express this one out, you can either express it out as P into bracket AI all over H dot PH, because the one at the bottom must suffice, or P into bracket AH all over AI dot PAI. So this one now, you know, we are talking about priori and we are talking about posteriori, priori and posterior, like inverse probability. You know, this one, this AI all over H. The inverse of it will be H all over AI, right? So that's simply where we are going. So the inverse of it will be H all over AI. That inverse of it will surface at the other side. We can see it here, H all over AI. And it's the same thing surfacing for each term at the bottom. H all over A1, H all over A2, H all over A3. Because the one at the reason why we're having all this, because the one at the bottom must always suffice to the probability with the one accompanying it. So it's as simple. I just wanted to get it with these techniques. The simple formula starts from, the simple formula starts from, this is how you just get it and understand it well. It starts from PAI all over H. So this one is equals to P, the joint probability, A intercept AI intercept H all over probability of H. I thought the probability of H is the sum of exclusive events. So the probability will be the probability of the sum of each exclusive event. Just know that like that. This one at the top is called joint probability. While the one at this point, it is called the posterior probability of H all over AI. H all over AI, the posterior probability of this. The inverse, like the inverse probability of this. That's this. That's what they asked us to look for. So for us to do that, I told you that this one at the top, you can either express it in two ways. Is it that this one is equals to the product of these two, or the product of the inverse of this, which is this, times the probability of AI. It's as simple as that. When you know all this, you can easily get the rest, and eventually you arrive at this answer. Thank you very much. This is on Baye'S theorem. So we'll just quickly solve an example around this, and we'll call it a day. Thank you. Yeah, I want to check an example which will be displayed. The example is about, suppose that 5 men out of 100. Questions under Baye'S theorem always go in this form. Suppose a certain stuff out of a certain stuff. So we are having two different scenarios. Assuming we are having a male in a situation where there is, okay, we are having a factor we are considering such as age, and we are also having a gender we are considering between male and female. You know, we have to use things relating to Baye'S theorem. Supposing we are having those two events should be dependent on each other. Do you get? For Baye'S theorem, we only use it for dependent events. So let's proceed. So the question goes to us. Suppose that 5 men out of 100 and 25 women out of 1,000 are colorblind. They said a colorblind person is choosing at random This is how you solve the question. Note what I'm going to tell you now. It's very important. What is the probability of being a male, assuming male and female is in equal proportion? The last sentence they mention, always pay attention to the last sentence. The last sentence they mention in the question will form how to route your probability question. They say, what is the probability of it being a male? What? Being a male. So, what you'll be working with, the probability of it being a male will be probability of male all over the other condition we're having. Blindness, let's say color blindness, C. So this is what you are looking for. The fact you can be able to deduce what you are looking for is the solution to the problem you need. So the other things can always follow. Do you get? So they say, what is the probability of male occurring among the people that are choosing at random that are colorblind? So thank you very much for understanding this with me. So let's proceed. So this is the question they asked us to find. So we need to know some stuffs. We need to know the probability of male that we have. And do we also have female in the equation? I think so. Then we need to know the probability. If there's female, then we need to know the probability of female. If there is other probabilities, we need to know them. But in this case, the question doesn't give us, okay, there are also women. There are women involved. So they say, suppose 5 men out of 100. The probability of male, 5 out of 100. So that is giving us 5 over 100. So the next question, they say, 25 women out of 1,000 are colorblind. So 25 women, that of women is 25 all over 1,000 are colorblind. So I want to solve a question that will be displayed. They say, suppose that 5 men out of 100, 25 men out of 1,000 are colorblind. So what you will pay attention to is the question they ask you, the last sentence. They say, what is the probability of it being made when they say a colorblind person is chosen? A colorblind. We are working with colorblind. What's the probability of it being male? So if you take this shape, probability of M all over C, being male, the one that they mentioned last will be at the top. Male all over colorblind that you are choosing from. Do you get? So this is what we're looking for. So now we're also looking for what is the probability of male occurring. They told you the last sentence before we end. They say, assuming that male and female are in equal proportion. So the probability of male occurring in the population is 1 all over 2, half, since they are in equal proportion, because the total probability must be equal to 1. So probability of female is equals to 1 all over 2 as well. Do you get? So we now want to check the probability of male and female in the inverse proportions. Do you get? So this is what we're looking for exactly. So the probability of, now get this, I want you to understand so that you can be able to solve any other question apart from this. So the next question they gave us, they said, suppose that 5 men out of 100 men are colorblind. On the men's side, the last sentence they mentioned are colorblind. So that would be probability of colorblind over men. Do you get? Probability of colorblind over men is equals to 5 out of 100. So the next sentence they mentioned, they say, suppose 25 women out of 1,000 are colorblind. So this will give us P all over the women, the colorblind all over the women is equals to 25 over 1,000. It's as simple as that. So knowing all this, we can then go into our Baye'S theorem and solve straight. You get your answer. So for Baye'S theorem, the formula that we have, let that formula be in your head. Do you get? Let the formula be in your head. Since you have already known the question you are looking for, to derive the formula won't be a problem. Do you get? It won't be a problem. And we know the different things that are involved. A male and a female is involved, and color blindness is involved. So you can simply get your question that you're looking for. So this is the question. We have been able to identify the question we are finding. So to get the formula to use, this will be the probability of male that is color blind, as in this one. The probability of color blind that is male. I'm sorry for that English. Listen to the last sentence that they mentioned, because the last sentence they mentioned will be the one at the top. Probability of color blind that is male. So that's male all over color blind is equals to probability using Baye'S theorem. This will give us the inverse of it. That is color over M dot, the one that is at the bottom we follow. Do you get? Over, this one at the top, you repeat it again at the bottom. This one at the top, repeat it again at the bottom, because that will be your first start. From the bottom, we are starting from 1 up until n. So this will be your first start. So this will be your probability of C over M dot your probability of M plus what is the next order alternative? The next order alternative will be the probability of the ones that are women that are colorblind. So this will give us probability of women that are colorblind. Dot, the one at the bottom, probability of women that are colorblind. The one at the bottom will surface. Do you get? It's as simple as that. So we input all those values we have gotten before, then we get our answer. It's as simple as that. Once you know this basic, you can get any question on this. So our PC all over M is equals to what? That is the one that are men that are colorblind. And that one in the question was when we solve this, we see that one was equals to 5 all over 100 times probability of male is 1 all over 2, or divide by 5 over 100 times 1 all over 2 plus the other one was 25 over 1,000 times 1 all over 2. After solving everything, you'll be having 2 all over 3 as your answer. That's the probability of colorblind that is male. That's what they ask you to find. This is the simple answer to the simple question. So thank you. So we're moving to the next question. Okay, so welcome back to class. So this is another question on Baye'S theorem. We're going to check it together. It's a simple one. Don't look at it as complex. It's a simple one. For you to be able to solve this question, you have to redraw the table, because this one is just giving the event, not the probability of the event, just the event. So for us to be able to redraw the table to calculate whatever they ask us to calculate here, we have to know the total numbers that occur at the last corner of the table, which is 100 here, right? So, and divide all units by it. All units by it. So, let's redraw the other table. So, still on that same question, I just divided everything by the last digits here. So, that's why we have everything here. So, fake notes. What you have here, the sum of this stuff should be equals to this. The sum of this should be equals to this. Take note of that. So, this one we have at this point here is the probability of C. C is the one at the end. Probability of C is equals to the sum of these two probabilities. Do you get? That's why we have 0.6. This one here is probability of D. So the sum of these two probabilities, that's what we have here. While this one here, the probability of A, the sum of these two, that's what we have here. Probability of this, the sum of these two, that's what we have here. You always confirm that to be sure that you're on track. So progressing forward, the first question they asked us to find, what's the probability? This was the joint probability of B and C. That's the first question. So it's as simple as that. You can get it easily from the table. So probability of B intersect C is where probability of B intersects the probability of C, which is, this is the probability of B, right? And this is the probability of C, right? Here the both of them intersect and meet. Here, this point. Where C and B intersect and meet is this point. So probability of B intersect C is equals to 0.35. It's as simple as that. But for the next one, we are going to see whether it's also simple. The next questions we'll be checking on that. This will also be seeing whether it's also simple as that. Because there are some questions that will give you that are dependent. There are some that are independent. You can only tell when you approach it this way. Assuming this question is independent, whatever we'll be having as probability of A times probability of C of, let me say probability of B times probability of C should be equals to probability of B intersect C. If this is equal, we know the event is an independent event. So we can easily check. Let's check if this is an independent event before we proceed forward. What's the probability of B? Probability of B is 0.35, right? Yes, it's 0.55. And what is the probability of C? Probability of C is 0.6. So times both of them together and see the answer it gives you. I'm quite sure that it will not give you 0.35. I'm quite sure it won't give you that. So that is to tell you that this particular question, it's independent, is a dependent probability. It's not independent. If it's independent, it will give us this. So to solve the next question better, the next question asks us to find probability of B depending on C. The next question asks us to find probability of B depending on C. So if I solve that, you can be able to solve the rest. That's just what I want to solve. Then you can solve the rest question that follows. So from the table, we're going to get the probability of this it. So now they ask us to find probability of B dependent on C. You know from the base equation formula I gave you, whenever you see it like this will give us the opposite. This will be probability of C dependent on B, or aside this way, let me not go too deep on base. You know this one can also be written as probability of B intersect C all over probability of C. Confirm with me that I'm right on this. Confirm with me that I'm right. If you are following from the very start of multiplicative probability, you can be able to get this. Because when we express this out as this joint probability, we'll see that joint probability of B and C is equals to probability of B all over C multiplied by probability of C. I told you the one at the bottom must suffice. Do you get? So for us to be able to get this, since we have known this from the table, and this one we have also known from this place too, so we can easily get that. And that will give us what? Probability of B over C should be equals to, from this formula here, 0.35 all over, what's the probability of C? I told you, probability of C is this, 0.6. 0.6. Whatever answer you get is your final answer. It's as simple as that. As simple as that. So for the next question they asked us there, they also say we should find probability B over D. Let me just show you that one so you can do the other ones that follow. It takes the same shape. Probability of B over D. Probability of B over D. If you are a very smart one, you know that this one should be giving you probability of B intersect D over probability of D. And what's probability of B intersect D? Where is B and D meeting? Where is B? This B. And where is D? This D. Where there are two meeting? 0.20. So probability of B intersect D is equals to 0.20. While probability of D, yes, probability of D, this C, this D. Probability of D is 0.40. Probability of D is 0.40. So automatically our probability of B over D should be equals to 0.20 over 0.40, which will be equals to 1 over 2. Then you can be able to do the rest. So let's check another question entirely.
Thanks for watching.